And welcome back, folks, for class number 2 in week 14. So we are halfway through this week, and we've got 1 week after this, so almost there. PLC 14, I posted this, and it's a finals review, concentrating mostly on the thermo and optic stuff, just because that's kind of further away. And the idea is that I just picked a couple of the problems and asked for what's the answer to those questions. So it's just a quick thing, but hopefully if you want to spend more time doing it, it's going to be useful. But the actual PLC requirement is just 2 of those problems. And don't forget that homework 6 is due today, and there's a quiz posted. I think. I'm pretty sure it's there. Hopefully. I'll check one more time just to make sure. But don't forget to submit homework and deal with the quiz today so that we can move on. I will post homework 7, and that's going to be on stuff that we've been talking about: photoelectric effects, Compton scattering, and some more of the stuff that we're going to talk about today. Well, we've been through a couple of basic experiments, kind of considered foundational experiments, about why we think photons are a good model to the behavior of light. And especially with things like the photoelectric effect, where you're thinking about what would the answers to these questions be if light really was solely a wave. And the answers just aren't really melding with what the experimental results are. And same kind of idea basically with the Compton scattering, the idea of a collision, right? Well, you wouldn't necessarily think of a collision if you had a wave coming in that was a mathematical wave. So I wanted to take a few minutes to talk about what the difference in the models is when you're talking about waves versus particles, and extending out towards actual material particles. What can we say about material particles now that we have this this information, this new viewpoint on what light does? All right, so so we talked a little bit about some of the relationships and how to calculate things like the momentum for light. We've talked about the momentum of light and the energy of light. And if you look at the mass relationship from special relativity, if you look back at special relativity, you'd see that the mass squared was E squared minus P squared. And remember that this is in the C equals 1 unit. So if you were to write them with the C in there, it would look more like this, where you have MC squared, and then energy by itself and PC squared. And you can verify that those units will work out. But nonetheless, the idea with a massless particle such as light, if you think of photons, right, then you have basically 0 here. Photons have 0 rest mass. And therefore, and the reason is because there's never a rest. There's no frame that we can jump into such that we'd be going like, oh, look at the photon, cute little thing just sitting right there. Maybe if I poke it a little, it'll bounce. It's not. You can't jump into a frame in which light is stationary, because every frame. Remember, one of the basic tenets of special relativity is that every observer observes light as traveling at light speed, right? So it's that silly question, well, how fast is light going? Well, it's going the speed of light. Well, if that's the case, you can't ever jump into a frame where it's not going that speed, okay? So it has 0 rest mass because we can't we can't get into that frame and weigh it. Therefore, the light's momentum relationship is essentially that the energy of the light is the momentum times c. This is for light. Right? And well, I should be a little bit more general about that. This is going to be true for any particle, any messenger particle that has zero rest mass. This is true for anything with zero rest mass, is that that's the energy momentum relationship. And you say, well, what other ones have zero rest mass? Well, there's a couple. What's known as the gluon, obviously the photon, and there's such things like this. The neutrino is pretty close, but actually has rest mass, which is a pretty interesting thing. Anyways, that's a whole nother semester's worth of a topic right there. So this is the energy relationship between for light between energy and momentum. And so if you think about the way that we calculate the energy according to Planck, right? He would have said that the energy of a photon is going to be calculated by doing h times f. Well, we would have said that's the same thing as doing hc over lambda, right? Well, if that's the case, and I have the ability to say that the energy of the the energy of the photon is this, and then it's going to have a momentum relationship like this, then I should be free to say that this is equal to P times C for a photon. And so what you can look at here is that the interesting piece to this, that must be the momentum. We see then that the photon momentum can actually be calculated by doing h divided by lambda. Okay, so the wavelength of the light and the photon momentum are related. And if you are wondering, well, how can that be? You have a fair question there. Because you'd say, well, wait a minute, what's a wavelength? How can we talk about the wavelength of a photon? Right? Well, that's a question, right? It's kind of in how you think about it. Nonetheless, it seems to be a fruitful way to go. The photon wavelength, shorter and shorter and shorter. In other words, as the photon energy goes up and up, so does the momentum go up and up. So when you're thinking about light waves that are visible versus ultraviolet versus X-rays, well, you're going up in momentum because you're going down in wavelength, right? So right around the, say, 1920s or 25 or so, somebody said, what if this momentum relationship was not only restricted to just photons or massless particles? Right? The question is, could this be true for material particles? That was the idea. What if this was true for matter? And the fellow's name was de Broglie, and he postulated this, and nobody knew how to answer the question. In other words, he wrote this as his PhD thesis. And he submitted it to the faculty, and the faculty said, well, I don't know, is this true? Is this right? Could this be useful? So what do you do in that sense? If you're a PhD advisor and your student submits something, you're like, well, I don't know if this is true or not. Who should I ask? Well, they did what everybody would do at that point in time. They asked Einstein. So they forwarded it to Einstein. Einstein read it and goes, it's like that, what is it, the scene out of Gladiator? He gave him he goes, Einstein, what do you think? Okay. So we got a PhD. Thanks, Einstein. This is known as the de Broglie hypothesis. And there's really no, it's called a hypothesis because, right, that's what it is. It's a guess, as many things in physics and in general in science are. If you want to try and explain something that does not seem to fit within current frameworks, you have to go outside the framework, right? And Newton did that by talking about forces and talking about gravitation and action and reaction forces and things like that. He stepped outside of what people thought at that time. What did people think at that time? Well, they thought that Aristotle was true, right? The idea that there's four elements: earth, wind, air, and fire, and that fire goes up and then air does it, right? That was their thinking. And Newton had to come along, and certainly Galileo before him had to come along and say, no, let's go outside this and make something new. So de Broglie did the same thing. He said, well, what if this was true for matter particles? And everyone said, well, that would be silly. That would mean that matter particles somehow could be characterized with a wavelength. So let's examine what that means if we're talking about matter particles, such as electrons. Remember, h is an extremely small number if you're talking about the value of it in joule seconds, right? So if you take an electron, right, let's consider an electron, and we're going to do something like ask, okay, what if I have an electron traveling at 1 meter per second? Right? Can I calculate a wavelength for this electron at 1 meter per second? Sure, because it's slow, it's a material particle, that's classical, so we know how to calculate classical momenta. An electron moving at 1 meter per second. The momentum of the electron would be mass times v. Right? That's our classical definition of the momentum. It is non-relativistic, so gamma is basically 1 at this point. And we could calculate what that is, and then see if we could use that to figure out what the wavelength, effectively, what the wavelength of that electron would be at 1 meter per second. Right? So with that, we would be able to say then that, okay, if I took the lambda and I flip-flopped P and lambda, I would get H over P here. And that would just be the same thing as H over mv. Now, I could do this. I could do this in SI units. In fact, I guess I'll start with that. I'll start with doing that. Let's suppose we've got lambda here, and H has the value of 6.63 times 10 to the minus 34. Oops, 34 in joule seconds. So you know that within joules, you remember what the joule unit is. It's the Newton times the meter, and that's not meaningful really in the case of this, but it breaks down that way. So we'll have a meter unit left over from the top here when I divide out the mass and the V. So for an electron, we have this horrendously small number, 10 to the minus 30 kilograms, and a 1 meter per second. Okay, so if I look at this, if I just look at the units real quick, the Newton meter in here and the seconds are going to flop up here, and a Newton we know is a kilogram times a meter per second squared. So the squared seconds are going away. The meter goes away with that meter, and the kilogram goes away with this. So I'm left with meters because it's a Newton times a meter. And that seconds went away with the force units, right? So if we do this calculation, let's see here. I think I wrote down something to do with this calculation at a meter per second. Maybe I didn't. All right. Well, it's going to be pretty small, I can tell you that. We're looking at something, this is about 1, so that we're looking at something that's around 6 times 10 to the minus 4 here. I'll just say it's around. It's going to go a little bit up because it's less than that. So let's call it 7 times 10 to the minus 4 meters. Which is kind of astounding, right? In other words, the wavelength here is like what, 1/10 of a millimeter? That's, I don't know, that's kind of weird, right? So even an electron moving at a meter per second has a wavelength that could be, let's see, what's got a wavelength that's about 1/10 of a millimeter? Gosh, that would be in the kind of the far infrared, I think. Not quite in the microwave region, because microwaves are typically about centimeters or so. They've got to go up a little further than that. So it's probably in the infrared. That's pretty funny. Would it be possible to make an electron go fast enough such that its wavelength was something about the size, say, of an atom? Or what about a nucleus? Okay, because the thing here is that when the wavelength of something is really, well, let me step back for a sec. If you want to look at the wave nature of something, okay, how do you do it? Well, you can try scattering it off something. Imagine that you're looking at the waves in the ocean, and there's people on surfboards out there, okay? Or there's swimmers or whatever. And there's sharks and otters and other things. It doesn't have to be people. The size of these objects is much smaller, I think you'd agree, than the wavelength of the waves in the ocean, right? The wavelengths of waves in the ocean is probably around 10 meters, right? And I mean, maybe there's a shark that's 10 meters long. That would be kind of crazy, but people are like 1 or 2 meters, right? Typically. So the waves don't see them, right? The waves don't scatter off something that's so much smaller than its wavelength, right? But now you put a big rock in the middle of the ocean, right? Like you go over to, or you look at the concrete ship or the natural bridges, there's rocks in there, right? And you can see the waves come in. Now, the rocks still are kind of small compared to the wavelength, but they're more that size. So when you get waves scattering off objects, typically those objects are approximately the size of the wavelength of the waves that you're dealing with. So take that kind of reasoning and say, okay, what if I wanted to probe a nucleus? How could I do that? Well, I could actually make an electron with a wavelength so small that it was about the same size as the nucleus. And would that scatter off a nucleus and tell me something about the structure of the nucleus? It sure could, right? So I can do this with atoms and nuclei and things like that. So let's take a look. Let's take a look about finding out the wavelength and therefore the energy of a matter particle, like say an electron. I'm going to find the wavelength of the electron such that it interacts with other atoms, right? Okay, so fine. I think we could probably do that. Let's suppose that I have, instead of an electron moving at 1 meter per second, let's suppose it has a kinetic energy of 1 electron volt. Right? Let's suppose we have an electron with kinetic energy equal to 1 eV. 1 EV, I think you may not have the yardstick quite in place. I should say the meter stick quite in place here. 1 EV is not relativistic, okay? 1 EV. I mean, you're looking at kind of like this. Right? One electron volt is, yeah, it could be moving fast-ish, but it's nowhere near going to have relativity effects here. So this is going to be classical, This is a classical kinetic energy, which is equal to 1/2 mv squared. And if I rewrote that in terms of momentum, you'll see I've got an mv here. So really all I have to do is square the momentum and divide by 2m, and I will have the kinetic energy in terms of the momentum. If I flip that around, I can use that to find that the momentum, if I solve this for p, I'm going to move the 2m over and take the square root. And I'm going to have, well, ke, 2m times the ke, will be how much momentum the thing has. Now, if I know what the kinetic energy of the particle is, then I can find its momentum pretty nice and quickly here. Here's where I want to show you. So let me evaluate this at a ke of equal to 1 eV. Now, if I do this the same way as I did this, where I'm going to put in the mass of the electron in kilograms, and then I'm going to deal with this in electron volts, I'm not going to get very far, right? I'm going to need to think about a conversion between either going from electron volts into joules, or I need to convert the mass into some type of electron volt energy, right? So let's do that. Let's convert it. Let's do the second one. I want to show you how to think about making these expressions more easily usable. All right. So let's think about it this way. I'm going to put in an mc squared here instead of an m. Okay, that means I've basically multiplied the right side of this by c, and then I dragged it into the radical. All right, that means I have to divide by c somewhere. All right, so I'm going to keep that in the front here. I'm just going to put that in the back pocket. I'm going to put that over here. I'm going to go like this. And I'm going to have the rest energy of the electron in electron volts. And then I'm going to have the kinetic energy of the electron in electron volts. So it's going to be electron volts squared, square root of that, and that'll tell me what the momentum is. Well, not quite the momentum, I suppose, but it'll tell me if I move the p over here, I can have it be equal to p times c, right? And that can also be a total energy thing. But I'm not going to do that just yet. I'm going to wait. I'm going to put in here the rest energy of the electron. And that's going to be 0.511 times 10 to the 6th EVs. So most of the momentum is really coming from the mass of the thing moving, which is kind of a funny idea, but there you go. Evaluate at 1 EV. So this is 1 EV right here. I'm going to get 1 over C times the square root of 2 times 0.511 MeVs times 1 EV. Square root of all that. It's going to be some number, right? 0.2, and it's close to being, it's close to going away. It's not quite going away. But the idea here is I'm going to get a 10 to the third here, right, from the square root. So the momentum of this thing, let's see here. Did I calculate that or did I not bother to? I didn't bother to. Okay, great. So the momentum of this thing, I'm going to find it's going to be this number. That's 2 times a half. That's about 1. So it's around 1 over C, say 10 to the third EVs. Now, what are we going to do with this factor of C? Well, we're definitely not going to put it into meters per second and try to divide. Let's not do that. Let's try to move away from mechanical units like in a 4A sense. Okay. Let's just shove it into the units itself. Let's write the units of momentum as EVs per C. so that we know we still have this here, and it's just now kind of a new momentum unit. All right, remember that I erased back here, but remember that the momentum energy relationship of a photon is this. Therefore, the units should work out, right? If I want the units of P, it should be the units of E over C, and that's what I've got. All right, so the units of the momentum, and this is when C is not 1, right? If C is 1, then we can just ignore the C, and that's nice. But these are momentum units. And they are totally valid. That's an okay thing to do. Just move the C into the units. It keeps it there, but it takes away you having to convert it into something else, right? So that the units work. Those are the units, so it makes it easier. So if I now want to take a look at what the wavelength is for this situation, I have the momentum already, so I could really have just written lambda being h divided by the square root of 2mk, or ke here, I guess, right? Like so. I could write it that way. But I've already got this, and now look what happens. This is really cool. This is once again why we kind of do this system of units, which is kind of weird looking. H is a small number, but H times C is not that small of a number. It's a fine number. It's a great number. So if I take the units of these right here, and I go, this is H divided by 10 to the third EVs per C, well now why don't I just take that C and pop it up here? Because it's in the denominator, right? So why can't I just write it as HC divided by 10 to the third EVs? I can. Should be able to. And HC is a number we know. Therefore, I would say this is equal to 1240 divided by 1,000 EV nanometers over 10 to the third EVs. So right away, I know in nanometers, it's about 1.2 nanometers is the wavelength of the electron. And that's only with 1 electron volt's worth of energy. 1.2 nanometers. So this now this has a wavelength which allows you to probe the atomic structure of things, because atoms are typically kind of around that size. They're not really that size, but they're smaller. And this is kind of a bigger wavelength. But remember, you kind of only have to be in the neighborhood, right? And it wouldn't be too much of a stretch to make this something like 10 EVs. And then all of a sudden that's going to be even smaller, right? So having this relationship actually opened up a really interesting door to using matter particles as probes for certain sized structures. Because why? We can control what the wavelength of the electrons is, right? We can control the wavelengths of the electrons. All we have to do is have a voltage. And gosh, 1 volt, I mean, that's easy. Anybody can do that. Or 10 volts, no problem. And even with a 1 volt, potential difference, and I can accelerate my electron, it's going to have a wavelength that's small enough that I can hit an atom with it and see what happens. It'll scatter off it and see what, oh, look at that. Okay. All right, now, by comparison, suppose that I took, well, I don't know. Suppose that I wanted to see how much difference is there between getting an electron to go to fast enough to get to a certain wavelength versus getting photons to get to a certain wavelength. Like, how much energy are we talking? All right. So let's suppose that I want to get something to be somewhere close to this. All right. Let's pick something a little different. Or actually, we could just pick the same thing. We know that that's a 1 volt potential difference, right? This costs us 1 volt. Which is really easy because we have batteries that are 1.5 volts. No problem. So what about a photon? What about a photon whose wavelength is 1.2 nanometers? Right? Why not just probe the atom with light? Wouldn't that make sense? How much does it cost us? I don't know, cost is not quite the right word maybe, but what do we have to do in order to get a photon with a wavelength of 1.2 nanometers? Well, the energy of the photon then, we know is hc over lambda. And it's just going to kind of go a little bit backwards here, right? So this is going to cost us about 1,000 EVs, or 1 keV. In other words, to make a photon with a wavelength of 1.2 nanometers, we have to have the ability to have essentially the equivalent of 1,000 volts. Whereas with the electron, I need only 1. Way easier, right? So the idea of having matter be able to probe structures through wavelength interactions is huge. We can actually put forth very little energy and try to get things accelerated to small speeds and have them do stuff for us without too much problem. Okay, so that's part of it. I also want to talk a little bit about the uncertainty that arises as a consequence of this. Now, now you might be thinking about this and saying, well, hey, this is all really great. Wonderful job that I'm doing here for you. And I am, by the way. But it is, after all, I erased it down here. It is, after all, simply based on a hypothesis. It's some guy came along and said, well, what if that was true for matter particles too? Would that work? Do we really know that this is actually happening and this is a true thing? Have we got any? Well, yeah, we do have experimental results that tell us that this is the road. This is a path to go on. The results are such that they seem to indicate this is useful. This mode of thinking about matter is useful, right? Let's take it a little bit further and say, okay, if matter has a wavelength, then it has some type of wave characteristic to it, right? Okay. Let's shoot some matter through our good old double slit experiment. When we had the double slit experiment, what did we do? That was really the thing, if you remember back all those weeks ago. That was really the thing that had to take us away from the ray model, right? We were super happy with the ray model. The ray model was great. Mirrors, light bouncing off, lenses and the light refracting through, and refraction through from air into a water or plastic or something like that. And we could calculate the angle. Everything was great. We were 100%, we had everything figured out until we tried to make light go through a small slit. And then we found out, oh, wait a sec, that's weird. Why is it not just going in straight lines? It's in fact spreading out a whole bunch. That's not cool. So you might ask yourself, what the heck, man? And you'd be okay. That would be an okay thing to ask. But let's go back to the double slit. That's a classic experiment in which anything that shows interference has wave properties, and vice versa. If it has wave properties, it shows interference. So we can go back to the two-slit setup. And so what we'll do is we're going to think about this. I'm going to make the slits kind of large, but let's think about what we expect to be happening when we look at light, which we already know what happens with light. But now what do we expect when matter gets shot through this? All right, now it comes down to the idea of our mental model of these objects, okay? The mental model we have of the objects is kind of bimodal, right? We have the model of something that is a wave. If we think about something as a wave, what does that mean? Well, it has a well-defined wavelength. In other words, a mathematical wave extends to infinity in both directions, okay? And therefore, if I pick any two peaks and I measure the distance between any two peaks or two troughs or however you like to do it, I'm just a big fan of peak to peak measurements. I will find the wavelength, and it will be the same no matter which peaks I measure between, right? Any of these, anywhere. It will be the same because the wavelength of a mathematical wave is constant as it extends to infinity in both directions. All right? And because of that, we can say with certainty that there's a known momentum with that wave. Okay? So let's take a look back here. Here is a screen. Okay? This is the two-slit setup. Nothing's different. It's all the exact same thing. If I put a light source here, we know what we're going to get. Light source is shining light through here. We know what we're going to get. We're going to get a peak in the central maximum, right? We get waves coming through here. We get waves coming through here. And then based on the path length difference, they interfere. And they give us regions of fringes, right? Of brights and darks. So we'd say this is a bright spot here, and this is a dark spot, and then this one's a bright spot over here, and then this one's a bright spot over here, etc., right? This is interference. And it comes from an interesting situation. So if I think about, let's see. Well, let's before I do that, let's go back. Let's do the same thing again, but now let's do it with matter. Before I go and do mathematical stuff, let's do this first. All right, now I'm gonna. So this is for the wave picture, right? Waves coming through here. I'm going to go through, do the same setup over here with, say, an electron source, right? And here it is shooting electrons out. And, oops. And here's a screen over here, yeah, right here. Okay, so you might consider electrons to be bits of matter, right? Chunks of matter, and you'd be 100% correct in thinking that. It's like you're taking pens and throwing them through a two-slit experiment. Okay, not really, but as if it was a really small pen. It's a really small chunk of something, right? And you're throwing it through here. If you have the particles coming through here, what do we expect when we look at the pattern on the screen? Okay, with waves, we already know what to expect. We've already analyzed this to death. But imagine that I've got particles coming through here, right? Here comes an electron, and it's going through here. And we've got an electron, and it's going through here, right? If I slow down my source, so it's going, which discharging electrons at some regular rate, right? Really, I don't get two of them going through at the same time, so I really should be careful with how I'm doing this. But what my picture is, it's either going through the top slit or it's going through the bottom slit. I'm looking at what does one electron do. It has two possibilities. One electron has the ability to go through either the top slit up here or the bottom slit down here. right? So it could go through either one of those. What do we expect to see on the screen if it's particles that's coming through here? Well, if the electron goes through the top slit, well then a bunch of electrons could go through the top slit, not all at once, but like through repeated firings, right? Suppose I fire this thing 10,000 times. Well, there's going to be a certain number of them that are going through the top slit. If they're going through the top slit, then more or less they're going to land on the screen opposite the top slit because there's nothing in the way between these two. It's a vacuum in here, right? So it's going to go through here. It's going to land. I'm going to get a peak like right here, right there. Now, I am going to get some scatter because the electron doesn't necessarily have to go exactly this way. There's going to be width to this peak, like some of them might be coming out this way at a slight angle like that, or it might hit the top of this thing and suddenly end up way down here. I'll get different counts, right? I'll get different counts at different areas. But for the most part, most of them are going to end up basically, if they go through this slit, they're going to end up kind of over here. If they go through the lower one down here, they're going to end up kind of over here. Yeah? So it's going to look something like this, where I'm going to say, I get either a congregation of these things going through the top and ending at the screen up here, or a bunch of them that have ended up on the screen down here, having gone through the bottom one. Yes, there are going to be stragglers and outliers and things like that, but let's look at the majority behavior for now. Okay. So, this is what we would expect if it was electrons, right? Electrons are little chunks of matter. If I was throwing electrons through a two-slit pattern, through a two-slit setup, I would expect this particle pattern of either here or here, right? But ultimately, what happens is when we do this and we slow the electrons down, not slow them down, we slow our frequency down. So it's like, right? I'm saying, what if I shoot one a second, right? One per second. We notice a few things. Number one is that when I shoot an electron out here and I watch the screen, an electron definitely hits here. And it's a full thing. It's not like some of it hits up there, some of it hits down here, a little bit hits there. No, it's like boom, all of it's right there, right? It hits right there and it leaves if it's a phosphorescent screen, say, right? It leaves a dot on the screen right where it hits. And it never is the case that I shoot one electron and I see two things or three things, right? It's one out, one in, right? So I notice that. The second thing I notice is that with repeated shootings, right, I start to get a pattern. I start to get a pattern, but the pattern is a set of all these bright dots, okay? The bright dots eventually, in fact, give me this pattern. In other words, I'm going to have a lot of bright dots in this region here, none here or here, and then a bunch more bright dots up here and here, and then none here and here. And this is the pattern I get, okay? So you can imagine it looks, if I were to take the screen and show you what does it look like, if I go like this, right? If I take the screen and I kind of show it, it's going to have electrons that have landed in these spots here. Right? But not in between. So electrons have landed everywhere I've made a dot, but there are places where the electrons have not landed. And that corresponds to these destructive interference. And it in fact, reproduces this pattern really well, which is kind of astounding because electrons are little chunks of matter. So, therefore, you have to consider that this assumption is wrong. It doesn't go through either the top or the bottom slit. It must go through both as it travels as a wave. Now, the problem is here that we're trying to understand the behavior of something for which we have no experience. We have no analogies for this. We have something that gets ejected as a particle, right? Just like in the photoelectric effect. It gets ejected as a particle, or in Compton scattering. It hits the screen as a particle, right? It doesn't spread intensity here or there like light does, right? It hits as a particle. So we think it leaves as a particle, it hits as a particle, it's a particle. And we don't see the particle pattern. So there's something wrong with the way we're thinking about it. All right. The idea here is that it probably can be thought of as traveling like a wave after it leaves, having been a particle, travels as a wave and then recombines into a particle. How any of that happens is your guess is as good as mine. But suffice it to say that we are operating with very little to go on other than our experimental results. Let's do this. Let's modify this experiment just slightly. Let's say that you're not really happy. And I don't mean that in general. I mean with this experiment, with electrons giving you this pattern. You're just not happy with that. That shouldn't be the case. How can matter have a wavelength? How can matter interfere? And it doesn't even interfere with other matter. It interferes with itself, right? Because one electron does not go through either this one or this one. It goes through both at the same time, which means it's interfering with its own self and then producing an interference pattern on the screen. It's not interfering with an electron which is also at the same time passing through the lower slit. Because remember, we're only shooting these things 1 per second. So there isn't the possibility of having an electron go through that one and go through that one at the same time, because we're shooting them one at a time and we're not noticing that two are passing. So the electron giving the wave pattern here must be passing, a single electron must be passing through the slits, both of them at the same time. So what does that mean? Does that mean the electron kind of like splits in half, goes through this one and then recombines somehow, right? We don't know. Likely not, but ultimately we don't have any real good picture as to what is the situation here, okay? Imagine that you're not happy with this experiment and you want to know, hey, hold on, an electron goes through either the top slit or the bottom slit. Stop screwing around. I'm going to find out which one it is. All right. So I'm going to when it's leaving the source, I'm going to put a little flag. Say I'm going to have a spin-up electron. I'm going to keep track of all the spin-up electrons. Right? I'm going to say, okay, where'd you go? I can find where you're going. I can watch where you're going. Right? When I do that, indeed, this pattern appears. In other words, when I notice that the electrons with all the flag in them, I'm going to track where are they going. And we say, oh yeah, that one went through here, and that one went through there, and that one went through there, right? How am I doing this? Well, I'm probably just shining a light on here just to see, can I see it going through one of these or the other? Right? I have a little light right here. If I see a streak through the light, it went through the top slit. If I shoot an electron, I don't see a streak, it went through the bottom slit. And ultimately, yeah, I get this pattern back. But then I take away my light, and then that pattern shows back up again. So we run into yet another dilemma, which is that when we try to observe what the results of the experiment would be under slightly different conditions by keeping track of the paths of the particles, it changes the outcome of the experiment itself. It behaves like we are expecting it to do, right? I want to say, well, look, I want to track the path of the particle as it travels from here to here. And if I track it and it goes through here, I see it, and then it gives me this pattern with a big intensity here and a big intensity here and nothing else. Right? But that's not this pattern. If I'm looking for that, it gives me that. If I stop looking for that, it gives me this. So then you think, well, I'm going to be even more clever. I'm going to take the light that I was shining here to see which slit it went through. I'm going to put it behind the slits so that the electron has already made the choice of which slit it goes through, and then I'm going to look. Right? I'm going to say, it came through the top slit. I'm going to put a little flag on it and watch it go through. And indeed, even when you do that, this is known as the delayed choice experiment. Even when you do that, you get back to this picture. And furthermore, if you randomly select times when the light comes on, you don't look at every electron. Suppose that this thing's just firing electrons. It's just firing away merrily, 1 per second. Boom, 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 right? And I have a light back here, and it's waiting to see, well, it's waiting to like a strobe light. It's going to shine, and then I'm going to see which slit the electron went through. But I don't do it on every single electron. Maybe I do it on 1 out of every 5 or something like that. And then I go track. What I'm going to notice is that those ones I tracked, those 1 in every 5, when I shined the light, they fall into this pattern. The 4 out of 5 I didn't track, they look like this. What do we do here? This is ridiculous. We're completely influencing the outcome of the experiment by attempting to see what's happening. So there's a lot more to this. I don't want to spend too much more time talking about it, but there's a fantastic video by Richard Feynman. I'll post a link to it in the Canvas. And it talks about basically this. So if you have a spare hour, I think that's about how long it is. If you have a spare hour, or you can break it up and watch it in bits, he goes through this in really great detail. Not great detail, but like wonderful detail. Anyways. Okay. We can go back even further, one more step, and I'll leave you with this. We can go back to the light source here, and suppose that I'm emitting photons, right? I'm actually going to put photons through here. They do the same exact thing as electrons. They come in, they hit the screen as a dot, and then if you really slow the frequency of shooting down, right? So it's 1 photon per second, say, right? Which is not what we were doing with the laser. The laser's billions and trillions and gadillions of photons per second. This is, what do you, 1 per second? It's like ridiculous. But it's going to give you the same pattern. It's going to give you photon landed here, photon landed here, photon landed here. No photons land here, no photons land here. It's the same exact behavior. So this is giving us the idea that quantum mechanical objects, such as light and electrons and things that are small like that, all behave this way. And it's very strange, all right? I want to talk about the collision of our two models mentally, right? What's going on? When you think about the wave picture of something, and I was saying, look, you could measure a wavelength. The wave picture, right, extends to plus and minus infinity. It goes all the way out, and it's perfectly periodic every single right time like this, so that no matter where I measured between what two peaks, right, between this one, or between this one, I would get the same wavelength. If the wave isn't a perfect wave all the way out to infinity, then its wavelength changes, right? So that means if I measure the wavelength here, it's going to be different from something over here. But if it's a mathematical wave, it's perfect. It's the same wavelength everywhere. Notice what that tells us. It tells us that with a well-defined wavelength, I have a very well-defined momentum. Right? If I have a very well-defined wavelength, I have a very well-defined momentum. Now, let me look at a particle. The particle model you've worked with since 4A. Right? This is the assumption that all of the mass is at the center of mass of an object, and we just track the center of mass. Right? That's basically the particle model. The particle model if we're thinking about a mathematical particle, it has no size, right? This is not really true. I've drawn a dot here just so you can see it, but a mathematical particle is like a mathematical line. There's no finite extent to it, right? It has zero size. Nonetheless, imagine that, and you could imagine that something very simple, like you're at a baseball game and there's an outfielder catching the ball and is throwing the ball in, and you suddenly take a picture of the ball while it's in flight. So your picture would have things in the background that you would then be able to say, the ball right then is here at these coordinates. So with the particle model, I'll be able to say the particle is there. I can measure its position very, very well. It just has a well-defined position. Right? Because that's what a particle is. It's right there. However, from my one single photograph, I can't tell which way the ball's moving. Right? If I don't have any other visual cues, like the fielder's in the shot and the arm's like this, and then there's a person waiting to catch it or something like that. If I don't have any of that in the shot, I just see a baseball and it's right there, and then there's a background. I can't tell if it's going this way or this way or this way or this way or this way, right? I don't have any idea of its velocity, which kind of corresponds to its momentum. So we would say it has a very well-defined position, but a very ill-defined momentum if I just take a quick snapshot look at it, right? So it's not well-defined if I look at momentum from a snapshot point of view. Right? And even on the board, right, if I drew this as this is your snapshot right here. There it is. Which way is it going? You don't know, but I know it's right there. What about the wave? It has a very well-defined momentum. But what is its position? Well, this wave extends mathematically out to infinity and minus infinity in both directions. So how can it have a position? It has a very ill-defined position. Oops, defined. Position. You see, those go together and these go together. You see that they're opposites, right? The wave has no real clue as to where it is, but has a particular wavelength and therefore momentum, whereas the particle has a well-defined position, but we don't really know where it's going. These are the two models that are basically colliding in front of us. We're trying to apply this or this, but in fact, it's not either one of these by themselves, right? It's like there's a third model which is taking bits of this and bits of this, and we don't know what it is. We don't know how much of this or how much of this, and we don't know when it stops being that, right? Because ultimately a baseball acts like a particle, and baseball is a bunch of electrons and protons and neutrons, and those are all these things that are together. The third model of quantum things. All things are made up of quantum things, but when does the quantum picture stop and the actual mechanical classical picture start? Well, we don't know that either. See, it's just like I don't really know what to tell you. We don't know anything. And this is physics. This is what you get used to. You just don't know what's going on. So we realize that if I take a piece of both of these, there's a level at which I can know the two of these things together, and it's called the uncertainty principle, and it was first thought up by Heisenberg. And it's just a result of our two models colliding. This is known as the uncertainty principle. That we can't actually measure both position and momentum of a quantum object to any precision that we want. There is a fundamental limit. So that gets into a whole nother can of worms. I'm going to put infinite precision here. But of course, that's not really true. I mean, of course it's true, but it's not really what I'm trying to capture here. The uncertainty in X, which we would call delta X, and the uncertainty in P. Now this momentum, let's be honest about this here. This P is in the same direction as the position along an axis. So this should be X in the of the momentum here. This is not the Y momentum. There's no uncertainty between the Y momentum and the X position. It's between the X position and the X uncertainty. And then its position in the Y with the Y momentum, and then the Z position with the Z momentum. They go together in pairs. It has to be at minimum, well, it's going to be greater than or approximately equal to H, meaning that I can't measure both of these to zero, I can't have both the uncertainties be zero. Or even small. They can't both be really, really small, such that when I multiplied them, it came out to less than H. There's a fundamental limit. It has to be at least this much. So if you're operating at the bare minimum of uncertainty, then when you find the uncertainty in these two quantities, it should be about equal to this when you multiply them, the Planck constant. I was just going to say something else about this too. What was it? Oh, darn. All right. So I was talking about the idea of when does the quantum mechanical picture stop and the classical picture start. In other words, right? You walk through doorways, right? That's kind of like something passing through a slit, yet you don't suddenly appear way over there. So our diffraction effects as we walk through a doorway are basically zero, right? We have no diffraction to speak of, because if you think about it in terms of waves, our wavelength is really small. Right? Our wavelength is really small compared to the size of the door. The door is like a meter. Our H over M, should be H over MV to find the wavelength, right? If I flip-flop these things, H over MV, and our masses are big, and our velocities are small, and H is a number around 10 to the minus 34. So our wavelengths are really small. Now you can imagine shining a laser light through something that's this big. It's not going to show diffraction. Right? Because you're not trying to confine the light, right? You have to try to squeeze the light down and make it go through a small opening in order for it to start spreading out on the other side. So if you consider our wavelengths as we pass through a doorway, our wavelength must be 10 to the minus 34 meters or so, which is, I mean, what is that? That's ridiculously small. That's smaller than the size of anything that we could possibly measure. All right. So the uncertainty principle is really this idea that we cannot measure both momentum and position to any precision that we wish. I'm going to have an uncertainty of this little bit in each one. No, you can't do that. There's a fundamental limit to it. All right, so let's do this. I'm gonna, well, you know what? I'm gonna pause here. We'll start talking a little bit about the Bohr model and the Schrodinger model tomorrow in the next video, and we're gonna take some of these ideas and see how they manifest when we look at the model of the hydrogen atom as come up with by Niels Bohr. And then we're going to look at it from the modern perspective with the Schrodinger equation, okay? Don't forget homework and quiz today. And with that being said, enjoy the rest of your quantum day, friends.